Welcome back everyone, and the boards are back. They look great, but my first error was apparent when I looked at the LED footprints. Although their outlines in the silkscreen don't overlap, the LEDs surely will not fit in there, so the footprint was misleading and I fell for that trap. Look at what I had to do. I couldn't put the LEDs side by side neatly. I wanted these old looking LEDs for a retro looks, but they would not fit, so I will change them over to an LED bar, which is more modern looking and it will look cleaner. So this was the first bummer, the first mistake in the physical design I made. This is an overview of the board, zooming into the power supply circuit. The operand drivers on the top. Try to look away from the LEDs. I made another mistake. You see there only one push button installed, the clock. The reset I didn't install because it turns out these buttons have reversed polarity. They are closed while they are not pressed, and when you press them you open them. If I had installed the reset button, the system would be in constant reset. For the clock it doesn't matter, it's up and down anyway. Now these chip-looking things that I will be pointing to right now, they look like chips, but they are not chips at all. They are resistor networks. I'm pointing at all the resistor networks on this board. It's much simpler and neater to use these networks instead of discrete resistors. Much easier to install as well. And I can swap out the value if I am not happy with them. I absolutely hate those LEDs. So two blunders in the physical design, both very easy to correct, as I'll talk about later. And I'll just give you now a couple of high-resolution snapshots of the board. If you can abstract away from the terrible LEDs, maybe you can still have some kind of aesthetical sense for how the board will look after the next interaction without those horrible LEDs in there. It wasn't designed for looks, it was designed for performance, but hopefully it will look good as well. And the yellow and blue are homage to Ukraine, in case you haven't noticed that yet. Now, the first electric test I did was to look at the 5-volt line with my oscilloscope in AC coupling, so I'm just looking at the noise. Now, this is not very representative because the board is not operating as its nominal clock frequency, so we don't see all the other effects. This is just to look at EMI, electromagnetic interference. And if each division on my oscilloscope is 50 millivolts, so the power distribution network is not picking up any interference, so that's good. I also looked at the clock line, the clock distribution network, pressed the clock button up and down, and the distribution network is fine. The levels are sharp, the transitions are sharp, there is no bouncing because I pressed the button, so that's approved as well. Then I proceed to repeat all the test vectors I had used while in the simulator, one episode ago if I remember, or one episode or two ago, and they all passed. So the logic design of this board is perfectly correct. There is nothing wrong at all with it, only two blunders in the physical design, the push buttons and the LEDs. Logically, the board is in top nick. Of course, we have to look at the electrical performance as well to see if those long traces that I had to use in this large board are not complicating things in terms of signal integrity. But before that, one more test of the logic. This is the shunt that, if placed, will put this board in system mode and ignore the dip switches, and that's exactly what it does. It's in system now. If I remove the shunt, then it goes back into manual mode and it's now a binary hand calculator. And the final test of the logic was to see if the bus outputs that are driven by those two 245s in there, those transceivers, right now they are driving 5 volt out on that particular line because all the lines are active, as you see there in the LEDs. But if I disable those transceivers, the buses should float. So I'll disable one of them and the bus should float. Let's see. And it floats. It goes to 1.5 volt, which is exactly what it should do if the transceivers are enabled, because they would tri-state and make the bus available to whatever else in Talos will be driving the internal buses. So logic is in top condition. Let's look at some electrical performance now. I connected a 2 MHz oscillator on a little breadboard. Through this green wire, it feeds a 2 MHz signal into the clock line of Talos through the backplane connector. The oscilloscope is measuring the output of the oscillator right next to its pin. So you see a well-formed, well-shaped clock signal there, 2 MHz. It goes into the board via the backplane. And now I'm going to measure it at the input of one of the transceivers. That's the transceiver that receives the clock signal and boosts it for everything else in the circuit. And you see that there is some ringing by the time the signal passes through the backplane connector, through a long trace, and finally arrives at the transceiver. So this is a comparison. You see in yellow the signal put out by the oscillator, and in blue the signal as the first transceiver sees it before it boosts that signal and distributes it through the entire board. It's important to make a measurement before and after the backplane connector, because that's the point of highest impedance mismatch. It doesn't matter if you measure it after that connector, close to the chip that receives it, or just after the connector on the trace. It will be the same thing, but on the two sides of the backplane connector it should be measured, and that's the difference you get. Now I'm going to measure the signal after it's boosted and goes through that 33 ohm resistor, and in blue now that's the clock signal that everything else will see on the ALU card. That's what the chips will actually see. And it's very close to the original signal in yellow as produced by the oscillator. The ringing is much attenuated by the 33 ohm resistor, although the levels are slightly attenuated by the resistor as well. But all in all, it's a pretty good looking signal. The ground cable of my oscilloscope is very long. It's adding interference to what you see on the screen. Things are better, but I didn't even bother to change to a smaller ground cable because, look, this result is already excellent. I know I can proceed with this design style. In yellow, that's the signal arriving at the first transceiver on the Talos card, and in blue is what all the other chips will be seeing across the board after the signal is boosted and treated to reduce ringing. And finally, global comparison between the signal as it comes out of the oscillator and the clock signal as all the chips except the first transceiver are seeing after the signal is boosted and treated for ringing. So this is excellent. I don't need to test it further. I will proceed with this design style. The board is looking great electrically. Okay, here are the new schematics with changes based on the lessons from this botched prototype exercise. The first main change is here on this part of the schematics. I swapped the two push buttons around. This one used to be reset, now it's clock, and this one used to be clock, it's now reset. And the reason is, if you follow the schematics, this first button here is inverted once, 6A to 6Y, that's one inverter gate, and then again 5A to 5Y, so it's not inverted at all. And given the fact that this button is closed as it is left alone, and when you push it you actually open the contact, this should be the clock, because it's the clock that we don't want to logically invert. So if I'm inverting it twice, it cancels out, it's not inverted. So if I'm not pushing the button, the clock is low, and if I do push the button, then the clock's high. And the logic works like this. Since this button is by default closed, then this point here is at ground potential, and this capacitor is discharged. So we have a low. When you push the button, then it opens. Now this is no longer ground potential. This will be charged through these two 10 kilo ohm resistors. This capacitor will be charged, and this will be a 1. And that's what we want. I want for the user, when he pushes the clock button, for there to be a transition from low to high. And when the user releases the clock button, it goes back to low. And reset, it's the other way around. Reset we have to invert, because in its natural state, at this point here, this capacitor will be discharged since this switch will be closed. And this point here will be at a low, and reset is active low. So the system will be always in reset if we don't press this button, which is not what we want. Therefore, it goes into 4A and comes out of 4Y, which is an inverter gate. And now it's by default high, so the system is not in reset. And when we push the button, this contact is released, the little capacitor charges from VCC via this 20k ohm to pair of resistors. This becomes a 1, and the system gets a 0, which is a reset. Reset is active low again. So that's the first change. Instead of changing the traces, I just swapped around the meaning of the buttons, and I did change the traces in the sense that I swapped these two lines around. The one on the top used to be reset, the one on the bottom used to be clock. I swapped them around, and the 33 ohm resistor that is supposed to attenuate ringing in the clock line, it has moved one level up. Another change is this. I've added this, and that's for the following reason. As I was using the prototype, I realized I didn't put LEDs to indicate the values of the control signals. I mean, in principle, you know them by just looking at the dip switch. It's on and off. But it's always nice to see that electrically the values are what you set them. So for the same reason that I use LEDs to show the values of the operands, even though you define them through dip switches, I decided to do the same for the control signals. There was space available on the board, so why not? And that just involves adding one more transceiver, which is here working as a driver to drive the LEDs, one more resistor network of 8 resistors of 1k ohm each for current limitation. And now I'm not using discrete 5mm LEDs anymore. That was an experiment that didn't work, obviously. I will be using now a LED bar with 10 LEDs. Why 10? I only need 8. In this case, I need even only 7. It's because bars with 10 LEDs are much more common. They're also cheaper. If I would go for a bar with 8 LEDs, there is only one available on Mauser, and I don't want to be, dependent on that one manufacturer. I don't know how long it will last. So we use 10 LEDs, and the 2 most significant LEDs never light up. So they go unused. That's all there is to it. In this case, even the 3 most significant LEDs, they are all wired to ground, as you see here below. So that's pretty much it for this part. I've done similar changes for the rest. This is the operands, that's all the same. The indicators, instead of discrete LEDs, now we have 4 LED bars, which are smaller, more elegant, fit in the board much better. The arithmetic is unchanged because it just works. I mean, the whole logic just works. I just screwed up the physical part, which is the part I'm not enthusiastic about. So I often screw up on things that I'm not enthusiastic about. The flags is the same thing, except that I now have an LED bar instead of the discrete LEDs. And the result, again, the same thing, except for the LED bars instead of discrete LEDs. So the only thing that changed more or less electrically is this addition here. Well, you could say that's just visualization. It's this addition here and swapping out the 2 buttons. That's basically it. And the result on the PCB is here. I've changed a couple more things as well at the PCB level. This part here, let me zoom in there. This is the new visualization. So that's the new driver, the new resistor network, and the new LED bar for us to visualize the control signals, including reset and clock, because it's useful to see them if you're running this board manually. Here, instead of discrete LEDs, now I have 4 LED bars. This, and this. And down here as well, this is an LED bar instead of 4 discrete LEDs. And this are LED bars instead of discrete LEDs. So that part is simple. And then I added the chips, the chip ID I added to the silk screen. For every chip, I put the ID. I say this is a 74 HC245, this is an HC283, HC86. Because as I was assembling the board, I caught myself going back to the layout where I knew what is what, going back to the schematics and the layout to remind myself what chip was what. Now, not even when assembling the board by soldering, but when putting the chips in the sockets, I realized that it would be much more convenient, especially for people who haven't designed the board themselves, if I just identified which chip goes where. So I added this to the silk screen. Even the IDs of other parts, like the LED bars, I added the part number in there. And I think that's more or less it. I had to shrink a little bit the silk screen here because I used more board real estate for the new LED bar to visualize the control signals. I got some fantastic comments last time, as usual. I will highlight two. One of them was somebody who told me that if you put copper fill, and this is a copper fill, this is the VCC copper fill, here on the right side, you have the properties of the copper fill, and you can change the clearance. So the clearance by default is the same as the design rule, 0.25, actually 0.254. Which is a tenth of an inch. But you can change the clearance of the copper fill so the copper fill doesn't go into these narrow areas in between traces, which doesn't help. It just makes EMI more likely or crosstalk more likely. I talked about it in the previous episode, and I thought to change this the clearance of the copper fill and avoid the copper fill from going into these thin spaces in between traces, I would have to change the design rules, which are here, design rule, and then you have clearance in there, which right now is 0.254, I believe. There should be one more digit here, doesn't matter. And I didn't want to change that because otherwise I don't get copper fill in other areas where I do want copper fill. But somebody highlighted to me that you can change the clearance for the copper fill alone without changing the design rules. So I did change it from 0.25 to 0.35 millimeter. And now we don't have anymore, you see, for instance, here, this copper fill here doesn't go in between the traces anymore because the clearance, the higher clearance now prevents it from happening. So that's pretty nice. I solved a couple of the things that were bothering me. So thank you for that comment. I'm going to put a screenshot of the comment with the name of the commenter here on the screen so you can see it. Somebody else also said, because last time I even temporarily deleted the copper fill in order to see the traces better, and somebody said there is a way to make the copper fill invisible. I'll put the comment on the screen as well right now so you can see it. I don't remember the name of the person, but in that particular case, I can't seem to find an alternative on the property bar, or anywhere else for that matter, to make the copper area invisible. I know we can make layers invisible. If I click here, I take out the top layer. If I click here, I take out the bottom layer. And if I click here, I take out the silk screen. Only the holes now remaining, or the vias. So I understand that, but I couldn't find a property. Oh, here, copper. Is that it? Oh, no, but now I removed everything. No, that's not it, because this is just the copper layers, and if I make this layer invisible, I take away not only the copper fill but the traces as well. Same thing here. So that doesn't help me. Non-copper. No object. Let's see. Copper area. Oh, maybe that's it. Oh, yeah, that's it. I just found it. Thank you, sir. Your name is on the screen now. This is the way to go. I don't need to temporarily remove the copper fill. I can just make it invisible. I've found it. So it's not in the properties area. Let me put this back before I forget. So it's in layers and objects. If I click the copper fill and go to copper area properties, it's not there. You have to go here to object, and then it is there. That's convenient for anybody making videos to be able to make the copper area invisible for a moment. Even during the design process, I can imagine there are situations where you want to take away the copper area. So this is it. This is how the board looks like now. I am about to send it to the manufacturers to get a new board. But since I've been getting such nice comments, I will wait for 24 hours after the publication of this video to see if somebody has an interesting comment that I would like to see before sending it to the manufacturers again. So if you have some suggestion or some idea that you think is worthwhile to implement before manufacturing, let me know in the comments below, and I will hold back for a day. Now, one final comment. If I were working for a company, doing this design for a company, I mean, no company does a design like this today, but in a virtual world, if I were working for a company doing this design, I would keep on using the prototype board I already have in my hand because it's usable, it works. You know, I can even bodge the wiring of the two buttons, so I can have both buttons functional. It's a completely usable board, just looks ugly. So I would use it until final integration of all the cards, including the backplane, and running a first, full application on the system. Only then I would order this new board from the manufacturers, because you never know whether from this point until full system integration, I will have some other ideas about what this board should do. So why order another board already right now while I can still use the current prototype? It's fully functional. So I would never do that. I would wait until the very last moment. But I'm not working for a company. I am a hobbyist. I'm doing this for pleasure, and to help out, people who want to learn a thing or two about how to put a mini computer together, help out the museum. But also for my pleasure, and I don't want to stare at the current board with those ugly large LEDs out of position for too long. I don't get closure. So because it's a hobby and it's largely about my pleasure, I am going to order a new board. I want to have a clean board in front of me because that's how I will feel good. I will have closure about it and I will feel good about moving to the next step. So I'm going to order it, even though I will be running the risk that I will need even a third one, because I don't know, after I put together the control logic, maybe I will realize I want some different pipeline registers in here, or I want some other control signals to be there. So that risk is there. I am aware of it. It doesn't cost much to order 5 of these boards, which is the minimum amount, because it's just a 2-layer board, even though it's large. So I'm going to do that, but in principle, you shouldn't. You may be wasting your money. So unless you're doing this for pleasure as well, and you are confident that you're not going to break the bank if you need a third run, it's better to hold on to a prototype and use it for as long as you possibly can before getting a new one. So you guys have 24 hours. After that, I will order the new boards. Real life has come calling, so I'll be busy the next several days anyway, while I wait for the new board. And the next episode will be probably a very short one where I just show you the final, or hopefully final, ALU card with the proper LED bars and everything. It will probably take a couple of weeks, I don't know, three weeks or so until then. But I have other things that are pressing and I need to do anyway, so that delay would happen either way. So yeah, I hope you're patient and you wait along with me for that. Hopefully it will be rewarding, and I hope you've been enjoying, and I hope it's also been informative to you. So I will see you in a couple of weeks' time. Take care.